Okay, well, hello everyone. My name is Scott Grizzard from the University of South Florida. This is Calculus Fall 2020, Lecture 10A. And we are talking tonight about the mean value theorem. So last time, if you'll recall, we started the mean value theorem by talking about Rolle's theorem, and we used proof by contradiction to prove Rolle's theorem. So that theorem, if you don't remember, was let f be a real function defined on this closed interval AB. If f is continuous on AB, f is differentiable on the interior, and f of a equals f of b, then there must be some u so that f prime of u equals 0. So the analogy to think of is that if I have a pin here and it's at, 3 feet right now, the height, and then I toss it up in the air, and then I catch it, which I obviously didn't do. Let's try that again. If I have a pin here at 3 feet, I toss it up in the air, and then it's just not my night. It's kind of like with the Rays dropping baseballs today. Okay, so let's do this. I have this tape measure here. You can't see it because it's green. That doesn't work because there's a filter. I have this bottle cap. Why there's a bottle cap on my desk, I don't know. I toss it up in the air, and if it comes, if I start at 3 feet and I toss it up in the air and then it comes back down, there's some place where I reached a maximum height, and that's where the derivative was 0, right? Because I didn't interrupt it. I didn't smack down on it and made it not differentiable. I let it go and it was differentiable, and then it happened. So that was Rolle's theorem. If I toss something up in the air, there's some point where the derivative is 0, and if I let it come back down. All right, how do we feel about Rolle's theorem 1 to 5 from last time? Let's see. I don't know if the 1 to 5 is working. It does not seem to be working. This is sad. Okay. Well, you can type your answer in the... oh, there it goes. TA figured it out. She's faster than I am. Okay. So it's just this idea, right? If I toss a ball in the air and I catch it and it's at the same height when I toss it as when I catch it, there's some time, and I don't interrupt the ball so that, there's no place where I have a spike. There's some point where the derivative was 0, right? It went up and then it came back down. And somewhere in that distance, the derivative was 0. Right? The velocity was 0. So I have this idea here, and what we're going to do, so that was last time, and then we used proof by contradiction to do a bunch of things. So tonight, what we're going to do is we're going to prove the mean value theorem. We're going to state what it is. And then we're going to use it in some examples. And then we're going to prove this very important thing, which is that if I have if I have two functions whose derivative are the same, then then they differ by a constant. The vertical shifts. In other words, the shape of a function is entirely determined by its derivative. And the only thing that can happen is that they have different intercepts at different places, right? The vertical shifts of each other. Okay. And that's very big because I need that in order to prove the fundamental theorem of calculus, which, as the name suggests, is kind of important. Okay. So let's go ahead and now, this little picture here. Is there anything special about the fact... Oh, and by the way, there are nice notes now. So if you go to the files on, Canvas, let me show you where these are. So if you go to the files on Canvas, you actually can see, if you go to class notes, you come down here, there's a new one there, Contradiction, Mean Value Theorem. I just finished those today, so there are nice notes for this. There weren't nice notes for... there aren't a lot of nice notes for stuff in Module 3, but I did have this one all nice. So you can actually see this on Canvas if you're looking. Okay. Well, the point is that there's nothing really special, right? There's nothing really special about the fact what I have here is kind of a flat tangent line, right? But there's nothing really special about it, right? So if I kind of rotate this whole graph a little bit, if I just kind of tilt the graph a little bit, all right, I have this idea. Let me do that here. So let's this button here. So if I want to revisit this, there's nothing really special about the fact that that tangent line is 0. I can revisit this whole thing. So I have this idea of me tilting stuff up. Okay. So, you know, I had here, I had A was this, and I had this kind of, you know, A and B were this, and that made me a place that was there. So basically, because the line running from f of A to f of B was flat, this thing somewhere that was flat. Okay? But there's nothing really special about flat. Okay? And that's the big idea about the mean value theorem. There's nothing really special, right? If I have this kind of 45-degree angle here, right? This line connecting here, I should have a line that connects these two things at that same angle. There's nothing special about the fact, right? Here, f of A was f of B, but the idea is there's nothing really special about the fact that, right, here I've got a slope of 1, and somewhere here I should have a slope of 1. There's nothing really special about the idea of it being flat. And that's the big idea of the mean value theorem. Okay? So if I want to go ahead and say that, I'm going to say there's nothing really special about the slope of 0. If you think about it. Right, so this is Rolle's right here. And this is going to be MVT. Right, and that's the idea. So how do we feel about the big idea here, 1 to 5? That I'm just kind of, all right, so I have this idea of a flat line here and a flat tangent here. But if I had some other angle, or if I had some other slope here, I would have some other slope there at U. Okay? That's kind of the big idea. There's nothing really special about the fact that the slope was 0. Okay. Well, let's dig into this a little bit more, right? I've got an S of X here. I've got an M of AB. Let's put some definitions on here. All right. So recall the following. L of X equaled F of A plus F prime of A times X minus A was the equation, was the function form of the tangent line. Okay, and line tangent to F at X equals A. All right. So that was this idea that I had before. But if you look at this picture, I need something a little bit more, right? I need this idea of a secant line. Okay, if we look at the picture, I need the idea of a secant line. Okay, so we're going to need that in order to figure out what this thing is really saying. So let's do that. All right, so let's do this, the definition. Right, now, the secant line here, if I go for MAB, and I was doing old point slope formula, right? And I wanted to find the equation for that line. All right, I would do y1 minus y2. So the slope of the secant line. Right, so if I wanted to find this slope, I would do y1 minus y0 over x1 minus x0. Right, well, here I'm going to let, so this would be the slope formula. This would be the slope from 2 points. Okay, how do we feel about that, 1 to 5? A little pre-calc, college algebra, Wayback Machine. 1 to 5. How do we feel about that? All right, I have 2 points, and I have a line, and I kind of want to figure out what's going on there. A little Wayback Machine. All right. So let's throw this into the Wayback Machine, but now I've got some, so we're going to let x1 equal a, I'm sorry, x1 equal, it doesn't matter, b, x0 equal a, y1 would then equal f of b, and y2 would be f of a. Right, so the slope of the secant line is going to be this. So let's see here. Let f be a function defined on AB. And then I'm going to have then MAB is defined as f of b minus f of a over b minus a is the slope of the secant line of f from A to B. 1 to 5, how do we feel about that? I reached way back in my Wayback Machine here. I dug back there and I pulled this thing out. So how do we feel about that, 1 to 5? It's just kind of a definition there. Okay, and then what I'm going to do is be, all right, so now I'm going to define S, and this is going to have 3 subscripts, which you don't need if it's ambiguous, right? So SFAB, okay, of X is the function form of this line. Okay, so this is my slope. I'm going to have f of b, f of a, plus MAB, a x minus a. Right, so this is just the point slope of the secant line. Right, so this is the secant line of, so the line secant from A to B of F, or the line secant to F at A to B. All right, if I could say something. The secant line from A to B. All right. Okay. So this right here is the secant line. All right, and I'm just expressing it as a function. And if f, a, and b are unambiguous, then we write just s of x. Okay. All right. So let's look at this here. Let's look at our little, oops, it's doing that thing. Let's look at our drawing here again. If I wanted to rebuild what the theorem actually says, okay, from this picture here, let's see. I'm going to look at Rolle's theorem, and the idea is that I'm going to keep this, and I need that. But I could ditch this part of it right here, and replace this with my new bit, with my new slope. Right. So here's the idea. What I'm going to do, I'm just going to paste this right down here. And I'm going to look at our picture. And I don't know why it decided to get rid of the. Hold on, it got rid of the mathies. I want f. I want this. I want this. I want this. I don't know why it got rid of them there and not here, which, you know, oh, it kept the, oh, I see. It didn't actually keep my mathies there. It just kept the symbol. Doesn't like that. Oh, it did like that. Okay. So what I've got is I've got Rolle's theorem here. And now what I'm going to do is kind of just go through and say, well, I'm going to kind of go through here, and I'm just going to edit it a little bit. I'm going to go, okay, MVT. I'm going to keep everything else, don't need you. And then I'm going to get rid of the 0. I'm going to say MAB. Okay? And that's the kind of thing that corresponds to this picture. So 1 to 5, how do we feel about that? So it's the exact same picture almost. I've just kind of twisted it a little bit. Okay. All right, so let's just write it out. Usually we put Cauchy's name next to this, but then your book calls Cauchy's mean value theorem something a little different in the back, and I don't want to confuse you. So usually this would have Cauchy next to it, but it doesn't in your book because your book reserves that from somewhere. So I say let f be a function defined on the closed interval AB if f is continuous on AB and differentiable on the open. There should be an if there. Then there exists u in a b so that f of u, f prime of u equals m a b. And then, you know, because I am good, I'm going to say we call m a b equals f of b minus f of a all over b minus a. Or you can do the other way around, because they're the same thing. Right, if I put f of a in front, f of b on this side, but then I also switch the bottom, I've multiplied both the top and the bottom by -1, which is just fun. Okay, so that's our statement. How do we prove it? Okay, let's prove it. So what we're going to do, all right, in order to prove this, we need Rolle's theorem. Need Rolle's theorem. And a differentiable in a continuous on the closed differentiable function so that g of a equals g of b. Differentiable on the open. I need something continuous on the closed, differentiable on the open, so that that thing works. So how do we feel 1 to 5 about what I would need in order to do this with Rolle's theorem? Okay, so that's the trick. I need such a function. Well, if I look back up at my chart, what's the difference between this and this? And I mean that as a pun. What's the difference between this picture and that picture? What is the difference between this f and this f? Literally, what's the difference? What is the difference between this f and this f? It's the secant line. No, really, that's the difference. If I subtract this function from this function, I wind up with the function that's the secant line. More to the point, if I subtract the secant line from this function here, I wind up with that function. No, really, the difference is the secant line. Really? I mean that literally. If I take the secant line, right? Let g of x equal f of x, minus s of x. Okay? Now, look at these lines. Look at these pictures here. If I subtract s of x from this f, I wind up down here at b. If I, yes or no? 1 to 5, how do we feel about that? If I subtracted the secant line from this f here, I would wind up here. So literally, the difference is the secant line. So if I do that, I can use that fact. I can use Rolle's theorem to get at this. Right? So the big idea for this proof is the difference is the secant line. Okay? All right, so let's just prove it formally. Okay. Let f of x so that f meets, so that f is continuous on AB and differentiable on AB, the open. I'll get rid of that. It's just let f, so that f is continuous on the closed and differentiable on the open. Recall s of x equals f of a plus MAB times x minus a, where MAB equals f of b minus f of a all over x minus a. I'm sorry, this should be b minus a. Okay. All right. So let's let g of x equal f of x minus s of x. All right. Couple things right to know off the bat. Okay. Since s of x is a line, s is continuous on AB and differentiable on the inside. Right? It's a line. It's continuous everywhere. It's differentiable everywhere. Indeed, since it's a line, and s prime of x is a constant. Don't know what it is the constant. Actually, I do know what it is. MAB, right? It's a line. Its slope is the same thing everywhere. So what I'm doing is I'm subtracting out s of x. Well, let's look at what these things are, period. Let's look at what g of a equals, well, f of a minus s of a. Okay, well, let's put s of a up there, equals f of a minus the quantity f of a plus MAB a minus a. You know, if I took a minus a, I'm going to get 0, aren't I? So let's see. This is going to be f of a minus the quantity f of a plus MAB times 0. Okay, well, that's f of a minus f of a plus 0 this week. That equals f of a minus f of a, and that equals 0. Okay, how do we feel about that, 1 to 5? Okay. Well, this is going to be a total shocker, but what happens when I do g of b? Well, I get f of b minus s of b, which equals, well, okay, f of b minus the quantity f of a plus MAB times the quantity a minus b. Well, it's not going to be as nice. Okay, this is going to equal f of b minus f of a minus MAB times a minus b, which is going to equal f of b minus f of a minus, I'm just going to put this quantity up here, f of b minus f of a over b minus a times a minus b. I just subbed in for MAB. Okay, a little bit of algebra here. I'm going to take that -1 and I'm going to multiply it right there. F of b minus f of a minus f of b minus f of a all over b minus a. Oh, I'm going to make that a plus because what I'm going to do is multiply this by -1. Oh, look at that. That's nice. That's nice. And I'm left with f of b minus f of a plus f of b minus f of a. Oh, that's convenient. Need a different canceling color here. Oops. Not that one. I think this red's too big. Oop, that one's too big. That's orange again. Let's go with this. So all those things cancel. And I wind up with 0. 1 to 5, how do we feel about that? This right here, I don't want to get like too lost in the algebra. Why do they cancel? Well, okay, so the b minus a's cancel because, you know, they're right next to each other and multiplied. So I took this negative and I multiplied it by a minus b. And that made this b minus a, right? That became negative a plus b. So the b minus a canceled. And what I'm left with, this becomes a 1 underneath, which is just 1. So I wind up with f of b minus f of a plus f of b minus f of a. This f of b cancels that f of... Oops. You're right. I screwed it up somewhere, didn't I? I forgot to distribute a negative. Where was it? Where did I forget to mess up? Where did I mess up my negative? I swear this is how it works. I literally just did this when I typed up the notes. Hold on. F of B minus F of A, that's correct. That one's correct, right? I distributed my negative. F of B minus F of A, that's good. This bit here, these two bits have to cancel. And they cancel when there's a negative 1. I literally just did this. I swear this is how it goes. Okay. Did I sub this in right? Oh, somebody already told me. Yes. This needs to be B minus A. Yes. Thank you, person who told me and I was ignoring you. Yes, that's right. I subbed it in wrong here. Right? This is X minus A. X is B. Okay. It's fixed. B minus A. B minus A. That took way too long. So this is still a minus. That's a minus now. That's a plus. Now they cancel and now they're equal to 0. Whew. Oops. Okay, now it works. All right, 1 to 5. How do we feel about that now that I fixed it? The X is A. I'm sorry, the X is B. I flipped it. Anybody? 1 to 5. Oh, there we go. All right. So algebra, after algebra hack, right? After algebra purgatory here, we wind up with this. Okay, so now it's fixed and we're happy. All right. Since S of X is a line, there we go. So G of A equals G of B, and Rolle's theorem applies. And by Rolle's theorem, there exists U in AB so that G prime of U equals 0. Since G prime of U equals F of U minus S prime of U, which equals F of U minus M AB, which equals 0, we have the whole thing. We have F of U, F prime of U. Oops, that should be there. That should be there. F prime of U equals M AB. Okay, so that's the whole proof. And the way it worked was this. Okay, so the whole way it worked was this. I created this new function, g, and then by subtracting out the secant line. And because when I subtracted out the secant line, I wound up, right, the difference between those two graphs was the secant line. So I wind up with g of a equals 0, and if I'm careful with my algebra, because remember, x is b, I wind up here with these all canceling here. So I wind up with 0 in both places. That means that there's a place where g prime of u equals 0, and g prime of u equals f prime of u equals s prime of u, right? That's 0. So I just moved the MAB over to the other side. One to 5, how do we feel about this proof and the big idea? The big idea here is that this graph here is the same as this graph, just tilted. So if the difference between the graphs is the secant line. All right, we're going to come back to the secant line. The secant line actually gives us a little bit more than just this. Okay, the secant line can give us a little bit more than it'll actually tell us something about concavity when I don't have a derivative. So we'll come back to the secant line. But let's just hang around here for a little bit. Let's use it. So I can use it to say things that don't exist. And there are exercises, by the way, that you should do, right? Find me a function where I'm continuous but not necessarily differentiable. And then find me a function where I'm continuous and differentiable on the open, but it doesn't apply, right? So I can find like little functions that have exceptions. And you'll actually do this on Friday in peer leading, because there's an exercise in this on peer leading for the MVT. Okay. But let's say I've got the following, okay? So suppose that, as an example, suppose that f is differentiable on differentiable everywhere. So that f of 0 equals 5. But f prime of x is less than or equal to -1 for every x. Prove f of 5 is less than or equal to 0. So here's the idea. And the big idea is I can't get lower than the line. Okay. In other words, I cannot get lower than this line. That's the big idea. So how do we do it? Well, suppose otherwise. And this is kind of how these MVT proofs go, okay? And the Rolle's theorem proofs. You just kind of go, well, suppose otherwise. And then you just like go after that. Now, you can do them without it. Even if you do it, try to do it without, you're really doing it with. The suppose otherwise is kind of underlying the pretty refrigerator proof, in a sense. Well, you can just do suppose otherwise. Okay. Suppose f is differentiable everywhere. F of 0 equals 5. F prime of x is less than -1 for all x. And f of 5 is greater than 0. All right. So what's true about this now? If I have this kind of suppose otherwise, what's true about this function? Well, the giveaway is that it's differentiable everywhere. That should scream to you MVT or Rolle's theorem if you had that condition, right? If you have f of a equals f of b, or you have some kind of root condition, prove that there's no 2 points where, that kind of thing, or that there's only one. If you see there's only one, your brain should say there's not 2. Those things should be lighting up in your brain. And if you see something like this, you should immediately go, suppose otherwise. Just because this begs you to say such a function can't exist. All right. So let's see. If f is differentiable everywhere, so since f is differentiable everywhere, f is differentiable, so my a and b, I'm going to say here, I'm going to set up Rolle's theorem. I'm going to set up MVT. So here I'm going to say let a equal 5 and b equal, a equals 0 and b equal 5. Right. Then f of a equals 5. That's that piece. And f of b is greater than 0. Now, since f is differentiable everywhere, f is differentiable on somewhere and continuous on a b. And bear in mind right now that this is 0 and 5. So, by MVT, there exists u in 0, 5, or AB. I can write AB here. Bearing in mind what A and B are, there exists a u in AB so that f prime of u equals MAB. Well, let's go ahead and calculate that. So I've got f of, I don't know what it is yet, right? I only know that it's bigger than something. Yeah, I'll do that. F of A, f of B minus f of A over B minus A. Now, here's a tip. Put the one with the inequality first. Okay? If I had a condition, so here, if f of A was the thing greater than 0, then I would write MAB equals f of A minus f of B all over A minus B. So what I've done is I've multiplied the top and the bottom by -1, but notice now my inequality doesn't have this weird negative sign in front of it, right? So I don't have to flip anything. 1 to 5, how do we feel about that? That's just a little tip. All right, you keep it simple. And in order to keep it simple, the thing with f of b, I mean, as simple as it can be. So the thing with the inequality, make that the thing on top with a positive. You will thank me later. It will save you from making 1,000 mistakes and sitting there scratching your head going, why would it work? And why would it work? And you're sitting there going, wait, I need to flip the sign here, but do I need to flip the sign? No. The one with the inequality gets it goes first, right? No negative oneness here. Okay, that's just a little tip. Back to the regular thing. All right, so I've got this here. All right. So there's some place where this is true. Well, f prime of u equals MAB, which equals f of b minus f of a all over b minus a. Now, here I'm going to introduce the inequality. Notice f of b is greater than 0. B is positive and on the top. So nothing changes. Okay, that's important. B is positive and f of b is positive and on the top. So when I do the substitution for the inequality, it goes in straight. F of b is greater than 0. So whatever this is going to be bigger than 0 minus f of a, which was 5, all over 5 minus 0. Negative 5 over 5, which is equal. I should put an equal, not a greater than, which is equal to negative 1. So f prime of u is greater than, it's not a greater than or equal, that's just a plain equal. The greater than is there, negative 1. How do we feel about that step, 1 to 5? And again, this worked cleanly because I checked to make sure that f of b, right, when I wrote it, f of b is the thing with the inequality. That goes first top. That goes front and top. So that I don't have weird things going on. Again, we're playing with inequalities. Let's keep them as nice as possible. We don't want mean inequalities. But u is a perfectly good x. So f prime of u is less than or equal to negative 1. So negative 1 is greater than negative 1. That is absurd. How do we feel about that whole proof, 1 to 5? So what was my strategy here for this problem? Okay, let's write it as if it was a regular proof for the strategy. What was my strategy? Assume otherwise, apply MVT, see what sticks. Okay, that was the whole strategy. All right. The thing with the inequality. That's important. Okay. So that's how these MVT problems, that's kind of the flavor of them, right? They're all proofs. Sometimes there's shows. Sometimes there's demonstrates, but they're all proofs. Okay, and the easiest way to get at them is usually to assume otherwise and see what sticks. You can do it other ways, and I'm for that. I just noticed that on my notes I did it with the. Oh no, I did it right. Okay. So you can, these have different things. But they're all kind of the same flavor. Okay, so let's do one of these. Let's look at some of its implications. And this is the big one. Okay. Its implications include, by the way, what we'll be doing next time, which is L'Hopital's rule. But its big one is this: if f prime of x equals g prime of x. This is the big theorem. If f prime of x equals g prime of x for all x and d, so let f and g be differentiable on interval d. If f prime of x for all x and g, d, then there exists a constant c so that for all x in d, f of x equals g of x plus c. Okay? So what I've just stated is if that I take two functions with the same derivative, they're vertical shifts of each other. Okay? So, example, x squared, x cubed, f of x equals x cubed plus 6, and f at g of x equals x cubed minus 6. Other example. Here's one. What is the derivative of arc cosine? Well, that's -1 over the square root of 1 minus x squared. 1 to 5, how do we feel about that? And then d over dx of, well, what's the derivative of negative arc sine? They're the exact same thing, aren't they? Negative 1 over the square root of 1 minus x squared. So, arc cosine and negative arc sine are vertical shifts of each other. Anyone know what the constant is? Constant, constant, constant. Anyone know? Anyone want to hazard a guess? Here are the two graphs. I'll put it over here. What is C? Here's arc cosine. Arc cosine is in blue. And that's green. And this one right here is arc sine. Okay. And the shift, by the way, is pi over 2. Okay. How do we feel about that? 1 to 5. Sorry, one of these is negative arc cosine, not positive arc cosine. This should be negative arc cosine, arc sine. Negative arc sine of x. And the shift is pi over 2. Okay, let's prove it. All right. Any questions, by the way? Okay. Let's prove it. So here I'm going to use that same magic trick like I kind of did before. Okay, so my strategy is going to be as follows. This shouldn't be in green, right? So I want to show that for all x in D, f of x, there exists some c, so there is some c. So that for all x in D, there we go. So I want to show that there exists some constant seed so that for all x and D, f of x equals g of x plus c. Now, the opposite of that, right, the negation of that conclusion is that there are 2 points A and B so that f of A minus g of A does not equal f of B minus g of B. In other words, I want to say they're not, if I want to say they are not vertical shifts, right? If I want to say they're not actually vertical shifts, that's what I want to say. 1 to 5, how do we feel about that? That's actually the hardest part of this proof, is figuring out what to assume otherwise. Okay? So assume the theorem is false. F prime of x equals g prime of x for all x in D, but there exists A, B, and D so that f of A minus g of A does not equal f of B minus g of B. So I'm assuming they're not vertical shifts of each other. Now, since f and g are differentiable on D, they are continuous on the closed and differentiable on the open. Now, let h of x equal f of x minus g of x. Okay? That means as a difference of differentiable functions, h of x, h is differentiable on AB and continuous on AB. So, by MVT, there exists U in AB so that f prime of U equals, I'm sorry, this should be H. H prime of U equals f of B, H of B minus H of A all over B minus A. Since H of B does not equal H of A, okay, right, because that was one of my conditions. So this is going to be H of A, and this is going to be H of B. There exists U in AB, so that H prime of U equals this. H prime of U does not equal 0. And that's actually all I need here. Now, however, h prime of u equals f prime of u minus g prime of u, which equals 0, since f prime of u equals g prime of u. Okay, so h prime of u does not equal 0, and h prime of u equals 0. This is absurd. There exists a constant so that for all x and d, f prime of f of x equals g of x plus c. And I didn't even need to hunt down the c, right? I just said there wasn't such a thing. What does that mean? Well, that means that there's two places where they're not equal to each other, where they're not where their differences are not vertical shifts of each other. And I just kind of flew with that. 1 to 5. How do we feel about that proof? That one's a little tricky. That one's a little what? Because it's got this kind of trick where I made an h, kind of like I did when I made the derivative of the kind of like what I did where I made the derivative of the other where I proved the mean value theorem, you know, where I took a difference between two functions. So it's not exactly straightforward, but it is kind of a nice, and it's an extremely important proof. The theorem is extremely important. We need it for to prove the fundamental theorem of calculus, part 2. So it, as I said, it's not the most straightforward proof, but it's one to think about. This idea that I could just subtract one function from the other. I could have written it a little better. As a matter of fact, I did write it a little bit better in the other notes. Okay. One last implication. The full power of L'Hopital's rule. And we will do that next time. We won't do the proof. So we've done L'Hopital's rule before, but kind of the diet version. The proof for the full version is in the back of the book. It's in Appendix D. We're not going to do that one. I mean, it doesn't really add anything. The diet version proof actually adds something because it warns you why both limits have to be 0. I mean, why the g and why the top and why the bottom both have to be going to 0. But the full version is not worth doing. But it is a consequence of the mean value theorem, the full proof. Okay, so today we actually stated and proved the mean value theorem. We proved the mean value theorem from Rolle's theorem, and we had this definition of a secant line. Keep that in mind, because we're going to need that again when we do concavity. As a matter of fact, I'm going to say that real fast, just as an aside. Secant line will be coming back. For concavity. Which is going to give us this nice generalization of what it means to have a concave function. All right, any questions? Okay, well, that's it for me tonight. I will see everyone on Wednesday, or for the quiz review, and then on. By the way, the quiz is posted, and then Thursday for the next class lecture. Bye.